Good afternoon, ladies and gentlemen. My name is Alex Moreno. I'm currently a PhD student studying electrical engineering and computer sciences at the University of California, Berkeley.
Hello, everyone. My name is Patel, and I'm an undergraduate at UC Berkeley studying electrical engineering and computer science.
We're both from the Berkeley Sensor and Actuator Center, and we'll be talking about the solar-powered crystal-free 802.15.4 wireless temperature sensor. So at the heart of this entire project, we're using the single-chip micro-mote, and this project came from the desire to reduce the amount of components. As you can see on figure 2, commercial off-the-shelf radio has many external components such as a crystal and passives. You can see that the single chip micro-mote only requires power and ground to operate. And there are many items on the single chip mote that were integrated, including an ARM Cortex-M0, an 802.15.4 radio, a Bluetooth radio, an ADC, a GPIO, and the list goes on.
So with this SCUM device, we've been able to demonstrate a number of interesting applications. One of them on the left is the lighthouse localization, where we're able to locate the SCUM chip within a centimeter cubed space using lighthouse base stations. We've also demonstrated SCUM integrated into sensor systems, including a dihydrogen sulfide sensor system, which uses the on-chip ADC. We've also demonstrated a number of interesting wireless capabilities. So as you can see on the top, we have a small PCB with the SCUM device on it, and it's able to communicate bidirectionally with an open mode device using the 802.15.4 standard. We've also been able to demonstrate transmitting Bluetooth low energy packets to mobile devices, as well as Bluetooth low energy packets to consumer iBeacon devices.
And so the main goal for this project was to power the single chip micro-mote from a solar panel and also still be able to transmit 802.15.4 packets. And to do that, we had to also compensate for temperature. So some of the problems that we're facing is that since we're using only a capacitor and a solar panel, we're very sensitive to large current draws. And we had to make sure that we didn't have a large current draw that would bring the voltage far down into the low 1.3 volts or below, because that would turn off the single chip micro-mote. Another problem that we face is that if we have large voltage drops, the crystal-free oscillator would also vary. And so that is one challenge that we had, and we can lose the channel that we needed to be at if we didn't calibrate appropriately. There's another dependence also for the oscillator with temperature. So as you can see here that there's a negative 40 ppm per degree centigrade for the 2.4 gigahertz oscillator, and a 160 ppm per degree centigrade for the 2 megahertz oscillator.
So our integrated system features 3 main components. We have the solar cell array, our SCUM chip, and a single 100 microfarad capacitor. The other capacitor you see there on the board is not used in this current setup, but will be used in the future for MIMS integration. So on the right side here, you can see a block diagram of our system. We have the solar panel connected to the SCUM chip, and we additionally have an optical programmer, which bootloads a program onto the SCUM device, and additionally is used for calibration. We also have an open mode device that receives packets from the SCUM chip, as well as a TNZ temperature sensor, which we use as a reference temperature measurement.
So the solar cells that we used, we refer to it as SAPI2, and it contains 3 unique solar arrays. One of them provides 119 volts, and this high voltage will be used to provide power for these high voltage buffers that we see on figure 10. And the 3.5 volt solar panel is used to provide power to the internal logic of SAPI2, including the finite state machine that we see in figure 10 on the bottom right. And also it provides power for the GPIOs for SCUM. The BBAT, the 1.8 volt solar array, provides power to SCUM. And so on figure 11, we also see that there is a large piece of electrical tape. We had to do this to shield the photosensitive electronics and thus reduce the amount of leakage. And for all the remaining slides, when we talk about providing power for SCUM, we are referring to SCUM receiving 560 microamps at 1.8 volts with 2 suns of illumination. Okay, so now back to that transient that we looked at earlier. So how were we able to make sure that SCUM stayed alive and didn't lose its program data? We made sure of that by going into this low power state to charge the capacitor. So we know that the capacitor can, or the solar panel can deliver 560 microamps. We made sure that the quiescent current was typically around 210 microamps by reducing the Cortex clocks to 78 kilohertz. So that allowed us to charge up the capacitor. So during phase 2, we go back to Cortex clock being equal to 5 megahertz as we prepare to transmit. And during phase 3, we transmit for a very short time to avoid the voltage dropping below 1.3 volts. And during phase 4, we're transitioning back to the low power state, and we're still at the 5 megahertz clock rate. And then we just repeat. And this allowed us to make sure that we didn't lose the boot state for SCUM.
So the first step in operating the system is bootloading the program. So in order to do this, we use a teensy device with an IR LED attached to it to optically bootload the program onto SCUM. So SCUM features an optical receiver that allows us to do this. And the optical receiver is also used during the optical calibration phase. So since SCUM lacks a crystal reference, we need to tune the on-chip CMOS oscillators in order for them to operate at the correct frequency. So in order to do this, we use the same teensy device with an IR LED, and that device sends 10 Hertz interrupts, which act as an absolute time reference for SCUM to measure and compare expected counts to correct the on-chip clocks. And so after this calibration phase is complete, we disconnect external power from the system, and now SCUM operates completely under the solar power with 560 microamps at 1.8 volts.
Okay, so now that we've talked a little bit about that, we also need to discuss how we're actually going to achieve the 802.15.4 standard. So we're working on channel 11, that is 2.405 gigahertz, and we have to make sure that the frequency has a 40 ppm deviance from that particular channel. And to do that, we look at the LO's architecture here on figure 16. We have 3 places where we can tune the coarse, mid, fine, and each of those has a 5-bit capacitive DAC. And so we're able to tune those in order to calibrate to the right 2.405 gigahertz that we need to be in channel 11. So there are 2 calibration methods that we have done previously. And the first one includes a interrupt that happens every 100 milliseconds. And in between those 100 milliseconds, we're counting with a counter, and we're comparing that to an expected count. And so we're able to tune the LO until we get the matching expected count from the counter. Similarly, for calibration method B, instead of using optical interrupt, we're using the packets received, and we're using a counter to compare to an expected IF value. So that way we're also able to tune the LO until we have the expected IF value from the counter matchup. So now that we have an idea of like, okay, this is what we need to do in order to reach the 802.15.4 standard, we started to look at ways that we can compensate for temperature. And we noticed the trend that the 32 kilohertz clock, as well as the 2 megahertz clock, has a positive correlation with temperature. So as you increase temperature, you also get an increase in the 2 megahertz clock count.
So in this case, we use the ratio of these 2 clock counts as a measurement to track temperature changes. So in this case, the first step we need to do is we need to take a measurement of the clock ratio, and we need to figure out which tuning settings of the local oscillator will allow us to properly transmit packets to the open mode device at a range of clock ratios. And so the range of clock ratios here corresponds to a range of temperatures. And so we continuously try different tuning settings and transmit packets. And on the right here, you can see a figure where each dot represents a packet that was received to this specific tuning setting. So now we have this chart, and it allows us to go between a local oscillator setting and a clock ratio. And the next step here is calibrating the SCUM temperature estimates. So we do a similar procedure and we measure the clock ratio. And then at the same time, we take a measurement from the teensy device and we can correlate those two and calibrate the SCUM temperature estimates. And so now that we can tune the local oscillator and we can calibrate SCUM's temperature estimates, we have our system fully functioning and we can go into a loop process where we measure the clock ratio, adjust the local oscillator frequency, make a SCUM temperature estimation, and then we transmit that over a wireless packet to an open mode device. And on the right side here, you can see a figure showing the reference temperature measurement compared to SCUM's temperature estimates.
And so after we did this a few times, we were able to get this temperature error plot. And we noticed that we have a standard deviation error of around 0.28 degrees centigrade. And for figure 25, we noticed that even though we have some temperatures having LC frequency offsets that are higher than the 40 ppm, we were still able to receive those packets with the open Mote, and we still had a 95.8% packet receivable rate across those temperature ranges. And so as a conclusion, we were able to demonstrate that we can transmit 802.15.4 packets over 35.5 degrees centigrade to 40 degrees centigrade. And also we were able to compensate the oscillator. And so future applications include detecting human fevers and detecting fires, doing outer space solar cells, and integrating with future MEMS devices, such as the gripper, the hexapod, the MEMS jumper, and the ionocraft.